Hello, I'm Nicholas, and I'd like to tell you about one of my favourite numbers, which is 1,701,936. Now, this is the number of distinct prime knots with up to and including 16 crossings. There was actually a paper written with this title in about 1998 by three knot theorists: Jim Hoste, Morwen Thistlethwaite, and Jeff Weeks. So mathematical knot theory is a branch of topology, which is the mathematical study of geometric objects under what are called continuous deformation. So stretching, twisting, rotations, but not cutting or pasting. And this goes back to 1867, when Sir William Thomson, who was later ennobled as Lord Kelvin, was inspired by the work of the German physicist Hermann Helmholtz on vortices in fluids, and also the experiments on smoke rings by a Scottish mathematician and physicist called Peter Guthrie Tait. And his idea was that atoms are essentially knotted vortices in something called the luminiferous ether. So this was a hypothesized all-permeating fluid that spread throughout the universe and was, amongst other things, the medium through which light waves and other electromagnetic waves travelled. And Kelvin's idea was that, for example, since sodium has two particular spectral lines, maybe that corresponds to something called the Hopf link, which is this simplest two-component configuration of two linked circles. So his friend Peter Guthrie Tait, along with two other mathematicians, Charles Little and the Reverend Thomas Kirkman, who was a Church of England priest, started systematically tabulating and classifying knots. And this is one of the diagrams that they came up with. And eventually they ran into two problems with Kelvin's lovely vortex atoms theory. One of these was that around this time, the Russian chemist Dmitry Mendeleev was constructing what ultimately became the periodic table of the elements. And unfortunately, there's no obvious structural similarities between the periodic table and the knot tables that Tait, Kirkman and Little were compiling. But actually worse than that, in 1887, two American physicists, Albert Michelson and Edward Morley, performed the celebrated Michelson-Morley experiment, which proved conclusively that the ether didn't actually exist. So this was very interesting, and unfortunately it killed off Kelvin's lovely, interesting, elegant vortex atom theory. But by that point, it didn't ultimately matter because mathematicians had already got interested in knots and they carried on working on them. They got their teeth into the problem and they weren't letting go. So mathematically, what we essentially mean by a knot, well, the technical definition is we say it's an ambient isotopy class of embeddings of S1 into S3. So what does that mean? Well, essentially what we're doing is we're looking at the different ways that we can fit a circle, i.e. a closed loop, into three-dimensional space. And we consider two such knots to be equivalent if we can sort of wiggle or stretch or otherwise deform one of them so that it looks like the other. As long as we don't do any cutting or gluing, that's allowed. So for example, here's a picture of the trefoil knot in two different forms. So essentially the idea here is that we take a piece of string, we can tie a knot in it, and we glue the ends together to get a closed non-trivially embedded loop in three-dimensional space. Okay, so knots are sort of three-dimensional objects, although actually if you talk to a topologist, they'll probably be a bit pedantic about this and say that really knots are one-dimensional objects living in three-dimensional space. But essentially we're viewing them as something that lives in three-dimensional space. And actually it's easier to represent them with diagrams on a two-dimensional page. But in order to make that precise, we need some formal way of relating three-dimensional knots and two-dimensional diagrams in a way that they behave the same and their notions of equivalence correspond to each other. So what we're going to do is we're going to use broken lines to denote crossings, like this. So here we have a strand going over the crossing and a strand going under the crossing. So this was all made formal, this was all made precise in the late 1920s by a German mathematician called Kurt Reidemeister in something that we now know as Reidemeister's theorem, although actually it was independently proved by two American mathematicians, James Alexander and Garland Briggs, around about the same time. So what Reidemeister's theorem says is that if we have two diagrams, they represent equivalent knots if one can be deformed into the other by a finite sequence of what are called Reidemeister moves. And there's three different types of these. So type 1 looks like this, type 2 looks like this, and type 3, which is slightly more complicated, looks like this. So a type 1 move consists of twisting or untwisting kinks in a strand of the knot. Type 2 move involves moving one byte or strand of the knot over another, like that. And a type 3 move involves moving one strand under or over a crossing. Now in practice this is actually more complicated than it sounds, and there were two particular 10 crossing knots in the Tate-Kirkman-Little tables that basically about 100 years later, in about 1973, were discovered to actually be equivalent knots. And this was discovered by a mathematician and lawyer called Kenneth A. Perko Jr., and we call this pair of knot diagrams the Perko pair after him. So actually we end up using and developing sophisticated algebraic and topological and geometric techniques for telling two knots apart. And essentially the idea here is that we define something called an invariant, a knot invariant. And this can be a number, it can be a polynomial, or it can be something a bit weirder and more esoteric like a group or something like that. And we want something that's in principle easy to calculate either by hand or by assistance of a computer, and we need it to be unchanged by Reidemeister moves. So what we do then is we take our two potentially equivalent knots, we calculate our chosen invariant for each of them, and we compare the answers we get. If we get a different answer for each, the knots are definitely not the same. They're definitely not equivalent. If we get the same answer for each, well, the question's still open. The knots might or might not be distinct. And in that case, we'll try a different invariant or maybe some different approach. So I want to show you a nice example of this sort of thing. The trefoil knot, which is the simple overhand knot with the ends glued together, is what's called tricolorable. And what this means is that we can colour the arcs of the diagram with three different colours so that at each crossing we either have three different colours represented or we have all the same colour. And it turns out that doing this, or being able to do this, isn't affected by Reidemeister moves. So any knot that's equivalent to the trefoil is also going to be tricolorable. Now if we try this for the figure 8 knot, which is the second most complicated non-trivial knot, it turns out that that's not tricolorable. And what that means is that it's not equivalent to the trefoil. So we know that however we draw these diagrams, the trefoil and the figure 8 knot are distinct, they're non-equivalent knots. Now using methods like this and using something called the Dowker-Thistlethwaite notation or some other notation for knots, we can actually get computers to tabulate knots. Back in the 19th century, Tate, Kirkman and Little did it all by hand. We can now get computers to do it. If we do this, we find that there's one knot with no crossing, and we call that the unknot. There are no non-trivial knots with one or two crossings, but there is a single non-trivial knot with three crossings, and that's called the trefoil. There's actually two different forms of it. There's a left-handed and a right-handed form. Each is a mirror image of the other. The figure 8 knot is the only knot with 4 crossings. There are 2 knots with 5 crossings, 3 with 6, 7 with 7, and the numbers keep going up as the number of crossings increases. And it turns out that in total there are 1,701,936 with at most 16 crossings, and many of them have quite interesting geometric, algebraic or topological properties. Thank you very much for listening, and I hope you found that interesting.